Hello class, this is section 3.8 and we are going to work through another eigenvalue problem example. The equation is the same, the endpoint conditions are a little different. We have y prime of 0 equals 0 in the left hand side and a y10 of 0 on the right. So first you have to consider the negative, 0 and positive eigenvalues, but the cases lambda not negative and lambda 0 can be ruled out as in the last video. So I'm not going to go through that again. It's going to work out exactly the same way. So let's consider the case where lambda is positive. Here we can make our usual substitution, y equals erx, and this gets us r squared plus lambda equals 0, or r equals minus lambda square root, or r equals the square root of lambda times I. And this means that we have a general solution of the form cosine c1 cosine root of lambda x plus c2 sine root of lambda x. First we have to take derivatives on both sides, and we have y prime equals minus root lambda c1 sine root lambda x plus root lambda c2 cosine root lambda x. So we can plug in our endpoint conditions now. For y prime 0 equals 0, we get that 0 is equal to 0 plus root of lambda c1, c2, and this just implies that c2 is equal to 0. From our second endpoint condition, we get that 0 is equal to c1 cosine root of lambda times 10, and the other part doesn't matter since c2 is equal to 0. So we have this equation, and we want to figure out whether we have one solution or if we have infinitely many solutions. And it's going to be important here whether cosine is 0, because if cosine is 0, then c1 can be any value, so we have infinitely many solutions. But if cosine is not 0, then c1 can only be 0. So the question is, when is the cosine of the root of lambda times 10 equals 0? So cosine is 0 whenever the argument is pi half or 3 pi half or 5 pi halves. So we need root of lambda times 10 equals to pi half, 3 pi half, 5 pi half, 7 pi half, and so on by the properties of the cosine. So root of lambda must be equal to pi 20th, 3 pi of 20th, 5 pi 20th, 7 pi 20th, and so on. And lambda itself must be equal to pi squared over 400, 9 pi squared over 400, 25 pi squared over 400, 49 pi squared over 400, and so on. In general, we can pick lambda equals 2n minus 1 squared pi squared over 400. So you see that lambda is just the odd squares times pi squared over 400. So 1, 9, 25, 49, these are all odd squares for n positive integer. Yeah, and for these values, the cosine is going to be 0, and therefore c1 can be anything. So these are going to be the eigenvalues. And when we have this eigenvalue, the solution is going to be y equals, so we have c2 equals 0, but c1 can be anything. So we look at this equation, plug in c2 equals 0. So y equals c1 cosine root of lambda x, and these are your solutions for any c1. To find the eigenfunction, we just have to pick one of the infinitely many solutions. So let's just pick the one where c1 is equal to 1. Eigenfunctions have to be non-zero, so you couldn't pick C1 equals 0. So there you have it. These are your eigenvalues, and each eigenvalue corresponds to this eigenfunction.